Okay, so here we go. So this lecture, so you know the details about Brownian motion. You know a little bit about ballistic motion. Yeah, so when you scale stuff down, viscous forces start to become really important and things slow down pretty quickly. A really up-and-coming area in science is motile particles. Motile particles means particles that can move, ideally by themselves. So self-propelling particles are very, very interesting. And so I'm gonna give you the basics of this. And there was one guy, he's absolutely brilliant. He gave a lecture in the 1970s. Her name was Cornell, and we come close to that. And he underlined a few thinking principles of what to keep in mind if you want to make a self-propelling particle. So I'll talk through the basic principles, and then you guys get given some time in order to come up with your idea of how to actually do this. And then later on, we'll get together and see whether it's actually possible or not. Okay. So we've seen before, things to keep in mind, that for large objects, obviously gravity really kicks in pretty hard. So, and then, you know, in Stokes' equation, you could calculate the thermal velocity. So where gravitational forces dominate, that is the left picture. And on the right picture, if you make things smaller and smaller, you go into the Brownian regime. Gravity kind of gets released a little bit. You get stuff moved around. The fusion coefficient was derived by Einstein, and with Smoluchowski and Langevin did some great jobs too. And he calculated this velocity. And then you had this initial ballistic velocity linking kinetic energy, half mv squared, to internal energy, half kT, if you look in one direction. And then you could calculate the initial ballistic velocity. So that's what we went through in theory last time. So if you want to move stuff, which is, you know, the ideal, what would be the best solution for self-assembly in micro machines, right? Be great if you have different components and you chuck it into a liquid and say assemble, like a transformer does or something. That'd be really cool on the small scale. Obviously, if objects are large, you can manually put it together. There's no real, you know, what's the fuss, right? You can build it yourself. But if stuff is really small, this becomes really complicated. So if you could do this, that would be really cool. The other thing what would be really cool, if you could make a little nanobot and you could swim around and probe and do all kinds of things in different environments. So what are the tools to move objects? So what do we know at this moment? Well, obviously, you could shake, yeah, on a large scale. You could steer on a large scale. If you flow something through a tube, you can speed up the flow rate, the velocity profile. We talked a little bit about laminar flow, but if you would increase the speed, then you get some turbulence and you can mix stuff. So here you see some turbulence flow in pipes at high Reynolds numbers. So inertia is important, yeah. And here's a little experiment that you can try at home in your bathtub, if the person that showered previously left it in a reasonable okay state. And so basically you get a piece of cardboard, you cut it out as a shape like this, and you put a little bit of detergent on the end of it, and you float it on water, and it basically launches itself. It goes very fast. And obviously if you're a little bit elegant, you can make all kinds of curves, and you can change the angle of this little gap there, and you could let it swim in circles until obviously you fully saturate the water with the interfacial tension. So you can have an interfacial tension gradient to play with. Then here you see thermal gradients. This is a picture, convective flow in the Earth's mantle. So there's some hot spots there, and you can see that when things are hot, they go up, and then when they cool back down, so you get a circular flow there. So there are tools that you can use in order to move stuff around. So now let's shrink stuff, yeah? So now let's look at low Reynolds numbers, at the regime when stuff becomes small, in a regime where inertia no longer matters, where viscous forces dominate. So, and then let's look at swimmers. So we first have to define a swimmer, and for the moment, we call a swimmer a creature or an object that moves by deforming its body in a periodic way. It's like an Olympic swimmer, right? So So I stated before that, if remembering what the Reynolds number was, it was basically means that viscous forces at low Reynolds numbers are way larger than inertial forces. In other words, inertia doesn't matter. Now this guy here, the picture of this guy, Purcell, gave this phenomenal talk in 1976, and it was published literally to what he said in the American Journal of Physics in 1977. And the next few slides, I literally took the slides that he used. So those diagrams, they're made by Purcell. Anybody has an idea who this guy is in chemistry? No idea. You've all done Spec Lab, right? He got the Nobel Prize for inventing NMR in 1952. Yeah? So, it's a pretty clever guy, and this is completely out of his area in a way, right? This was a random talk, and so it's pretty cool. So, he was interested in how could you swim on a microscale. So, and if inertia doesn't matter, then time doesn't matter. Yeah? That's kind of weird. And he started his talk off with the scallop theorem. So you have a scallop in a sea, it's a large object, yeah? And how does a scallop move? It opens its shell slowly and then closes it really quickly. So it will swim in one direction. Every time it closes it fast, it'll move, yeah? The same thing if you would swim in a swimming pool and you just use ordinary breaststrokes, yeah, you bend your legs and then suddenly, bam, you close them really quickly and you go in one direction. Now the fun bit is that symmetric movement doesn't work when inertia no longer matters. So if you would be shrunk to a micrometer and you would jump in the pool and you would swim the same way as if you would normally do, you would stay in the same spot. And the reason for that is that because time no longer matters, inertia no longer matters, only the movement matters. And if the movement is open-close, it's a periodic, it's the same movement. Going open is the same as closing again, which basically means the thing stays in the same spot. So you have to have an asymmetric type periodic movement in order to propel yourself. So ordinary swimming doesn't work. So here is what he came up with. So army knife at the top, pretty big thing. What if you would shrink this? So you have an object. Imagine this creature would exist. You have an object, you have two hinges. Yeah, the hinges can move on the right hand side, the left hand side. They can move up or down. And then you have, in a way, you have 5 scenarios. Scenario 1, 2, 3, 4, 5. Let's start with number 1. So both hinges are up. And then you're going to move the right hinge down. How is this thing going to move? Yeah, so you flap it down. And if you flap it down, you could say, okay, I'm going to move a bit to the left, right? So that's why this diagram is plotted here below. And then 2, you're going to basically pull the left one down, which means you're going to move kind of upward in that direction. And you're going to basically move again, and you move the right one up, back up, and then the left one back up. So you go down, down, up, up. And as a result of that, initially, you would think you would swim nicely in a circular manner, or in a, well, kind of spherical manner. The interesting thing is that people are still trying to solve this with numerical situations. Because the interesting thing, in his talk, he said, oh, you can work it out, but it's still not worked out properly. So, but in theory, this is one machine, or one organism, that is able to move via this way. Here's a few other ones. The one at the top, it's like a torsional kind of dense sausage in a way, and you can turn it in the same kind of direction, and as a result of that, it would move. The one displayed below is like 2 cells on top of each other, and if they would move by turning, the object would go into one direction. A little bit more, things that you could think of that also happen in nature are displayed on the right-hand side. So you could have a body and you have a flexible oar on it that just wiggles up and down in a randomly kind of fashion. Or the other way is you have a corkscrew. So it tumbles around and it forms this kind of propeller. Yeah? Those types of things could move, potentially, on the micron scale. And why? Is because you have an asymmetric type of periodic movement. Now, which of these kind of drawn things, you know, which kind of objects are you familiar with that could move? So you've got something on the micron scale. Do you know anything that can move on the micron scale? What moves on the micron scale? Exactly. As one example could be, well, is that going to move via, you know, flexible oar movement or a corkscrew movement? You know, so cells do move in certain ways sometimes, and so let's have a look at a bunch of these things and see what we get. So for that, there's a nice web link at the Rowland Institute at Harvard, and there's some really nice bacterial movements on there, and we're going to have a look at that for a sec before we continue with that. So for people online, they should just go to that web link and have a look at a few of the movies.